Today we will discuss Couchy theorem. Statement: if f of z is analytic at all points inside and a simple closed curve C, then we have integration over C f of z dz is equal to 0. Proof: let f of z is equal to u plus iv, then integration over C f of z dz is equal to integration over C f of z is u plus iv and dz is dx plus I into dy. Because z is x plus iy, dz will be dx plus I into dy. Next, that is integration over C f of z dz is equal to integration over C u into dx minus v into dy plus I integration over C v into dx plus u into dy. Just multiply term by term, we will get this equation. That is equation 1. Now we have Green's theorem, which says that if m of x comma y and n of x comma y are two real valued functions having continuous first order partial derivatives in a region R bounded by a curve C, then we have integration over C m into dx plus n into dy is equal to integration over R dou n by dou x minus dou m by dou y into dx into dy. Applying this theorem to the two line integrals in the RHS of 1, we have apply that theorem to equation 1. We get integration over C f of z dz is equal to integration over R minus dou v by dou x minus dou u by dou y into dx into dy plus I into double integration, this integration over R dou u by dou x minus dou v by dou y into dx into dy. Since f of z is analytic, we have Cauchy-Riemann equation. Cauchy-Riemann equations are dou u by dou x is equal to dou v by dou y, dou v by dou x is equal to minus dou u by dou y. And we have integration over C f of z dz is equal to minus dou v by dou x is dou u by dou y minus dou v by dou x is plus dou u by dou y. Similarly, minus dou u by dou y, this is as it is dx into dy plus I into dou u by dou x value is dou v by dou y, therefore dou v by dou y minus dou v by dou y into dx into dy. Dou u by dou x minus dou u by dou x is 0 and dou v by dou y minus dou u by dou y will be 0. Therefore, the integral value is 0. Integration over C f of z dz is equal to 0. Hence the proof. Next, we have the property, that is statement: if C1, C2 are two simple closed curves such that C2 lies entirely within C1, and if f of z is analytic on C1 and C2 and in a region bounded by C1 and C2 known as the annular region, then integration over C f of z dz is equal to integration over C C2, this is C1, C2 f of z dz. See the statement here: C1 and C2 are two closed curves such that C2 lies entirely within the C1. If f of z is analytic on C1 and C2 and in the region bounded by C1 and C2, this is known as the annular region, then we have to prove that integration over C1 f of z dz is equal to integration over C2 f of z dz. It is, we have to prove that two integrals are same here. This is the figure according to the given statement. C2 lies entirely within the C1. Okay, this is the path here. Next, let us introduce a cross cut in the form of a line segment PQ with the point P on C1 and Q on C2. Then the curve PRS PQT UQP as shown in the figure is a simple closed curve and f of z is analytic inside and on the boundary of C. Hence, by Cauchy theorem, we have In previous theorem we have integration over C f of z dz is equal to 0. We know that in this property C is split into C1 and C2. Therefore, since C is the union of the arc PRSP, PQ, TUQ and QP, the theorem becomes integration over C f of z dz plus integration over PQ f of z dz plus integration over minus C2 f of z dz plus integration over QP f of z dz, because here this C splits into 4 because here C is a union of arcs, these 4 arcs. Therefore, that integral is like this, which is equal to 0. That is integration over C1 f of z dz plus integration over PQ f of z dz plus minus, here it is we know that from the earlier property, if integration over minus C2 f of z dz is there, then it will be minus integration over C2 f of z dz. Apply that property here, minus C2 into C2 integration over C2 f of z dz. Here it is QP, take PQ, then it will be minus integration over PQ f of z dz. Here plus integration over PQ f of z dz minus integration over PQ f of z dz will be cancel. Remaining is integration over C1 f of z dz minus integration over C2 f of z dz. Take this minus term to this side, we get integration over C1 f of z dz is equal to integration over C2 f of z dz. This is the proof. Next theorem is Couchy integral formula. Statement: if f of z is analytic and on a simple closed curve C, and if A is any point within C, then we have to prove that f of A is equal to 1 divided by 2 pi I integration over C f of z divided by z minus A into dz. Proof: since A is a point within C, we shall enclose it by circle C1 with z is equal to A as a center and R as a radius, such that C1 lies entirely within C. The function f of z divided by z minus A is analytic inside and on the boundary of the annular region between C and C1. This is according to the previous property. This is the figure for the given statement. This is according to this statements. This involve the property here. This proof involve the previous property. Now, as a sequence of Couchy theorem, integration over C f of z divided by z minus A into dz is equal to integration over C1 f of z divided by z minus A into dz, which is equation 1. The equation of C1, that is circle with center A and radius R, can be written in the form, we know that if the equation of C1 is this equation of this circle with center A and radius R, we can write it in the form mod z minus A is equal to R, z minus A is equal to R, that is equivalent to z minus A is equal to R into e raised to I theta. Then z is equal to, take that minus A on this side, we get z is equal to A plus R into e raised to I theta, where theta lies between 0 and 2 pi. And dz is just differentiate this one, we get I R e raised to I theta into d theta. Using this results in this equation, 1, substitute. After that we get integration over C f of z divided by z minus A dz is equal to integration over theta is integration from 0 to 2 pi f of A plus R into e raised to I theta, because z value is A plus R into e raised to I theta, divided by z minus A is there, z minus A value is R into e raised to I theta, therefore it is R into e raised to I theta, and dz value is I into e raised to I theta into d theta. Next, simplify. Here I is constant, take outside the integration. The integration from 0 to 2 pi f of A plus R into e raised to I theta divided by R into e raised to I theta into R into e raised to I theta into d theta. R into e raised to I theta, R into e raised to I theta get cancelled. Here simply remaining is integration from I into integration from 0 to 2 pi f of a plus r into e raised to I theta into f of theta. This is true for any r is greater than 0, however small, hence as r tends to 0 we get integration over c f of z divided by z minus a into dz is equal to I into integration from 0 to 2 pi f of a, if r is 0 here, if f of a into d theta, here f of a is constant, I into f of a, theta is f of theta, simply integration of 1 is theta, limits from 0 to 2 pi, just apply the limits, we get integration over c f of z divided by z minus a into dz is equal to 2 pi I into f of a. Thus f of a will be f of a is equal to 1 divided by 2 pi I into integration over c f of z divided by z minus a into dz. This is the proof.